Hello, hello, hello. I am here ready to tackle Everybody Codes Quest 18. My first time, well, not the first time, I guess my first time in a while since I've been able to catch it as it's been opening. Hoorah for holidays. But yeah, ready to go. We will see how we fare. Considering these are the last days, difficulty might be going up or down. Who knows? Pathfinding, cool. 11 minutes. Not pathfinding, water filling. Okay, this is water physics thinking. Calculate how much time needed to reach all from the moment the channel is supplied with water at the edge point. So water goes in, 2, 3, 4. So it's how long until all things are touched. This feels like Dijkstra. 10, 11. So basically I just need to reach all of them until all are reached. So I get the locations of all palm trees. I do Dijkstras. And then I say math.max. What's the one that takes the longest? I got this. Okay, so let's only on this one. Let's get the world. This again. Ray of strings. Const. What is entry? Is entry always this one? Okay, so const start equals R1 C0. Const trees equals an array. And then for each plot R equals 0, R less than world.length. Same for C. But C, of course, is world R length. Then it's if world R C equals, put that equality in there. Not that equals P, then trees.push RC. Then we need to do another one to build the graph. So let's start with that. I got a feeling this graph might not survive too long. If it is a dot, then we can go from one place to another. Here we go, which means let's invert it to say not a dot to continue. Const ROCO of directions, which is 0, 0. Let's make 4 of these. Let's start with the first ones. So right, well, this is up and down, not right and left, apologies. And this is right and left. Const NR and C equals R plus RO, C plus CO. Well, we have to get the character first. Car equals, actually we don't care about it, we'll just do the conditional check. NR question mark dot and C equals a dot, then congratulations, we are graphing to it. That is graph, which is RC const from key equals plus C from key to key equals, it's just 1 really, so let's just do that. That's our weight. And then it's do const to key equals NR plus NC. Goofed this around. There we go. We have to make sure this thing exists. So if from key in graph from key equals an array, actually, right? So then we're just going to do the dot push to key. I have a previous Dijkstra, I'm going to go copy to do this. So we do this, we have the graph, we need to go find, nope, not there, previous Dijkstra. I do use a Dijkstra here, is this the right kind? Yes, this is the one I want. And yep, this is what I need. So let's use it. This returns the distances, and then I'll use that for other stuff. So that is distances equals Dijkstra graph start, which is start up. C, and then we have to go find the best of this. So that is let best equals math dot min. Well, not math min. Number dot min. So furthest, there we go, for const tree of trees. It's gonna be const furthest equals math dot max. Furthest distances tree dot r plus plus. I think I got it. Boom. Hey, why you no work? While I'll be down, let's turn that off. Get that back on. Expected nan to be 1. What? Okay, it means distances, guys, and undefined, which means we never made it to a tree because we're not allowing ourselves to go to trees. Oh, don't copy that. If you're going to a place or you're going to a palm tree, right? P for palm tree, P for palm tree. So that didn't happen again. Let's look at distances. So good. We got a couple that are still infinity. We got nans. What in tarnation? What? Did I not build the graph out? If it's not a dot, yeah, we can go from dots to palm trees. I guess we can go from palm trees to things. And not a palm tree. Okay, we'll allow that navigation to happen. Boom, we got it. The real one, which should be running. Oh, I put the only on that. Let's move it up. 109. Boom, we got it. Water bleed simultaneous. I was worried about that. Dang it. So it's Dijkstra from 2 different starts. I mean, I'm sure it's doable. It's not what I was planning for. I was slightly worried about it, though. I think it'll be okay. I just modified Dijkstra a little bit to take multiple starts. So solve quest 2. It's going to be a real copy of 1. Let's drop our log. Go for 2 starts. Now, are they consistent starts? If so, I can just, use that. Also, what's going on with this? Okay, I was being like, why are we not seeing big picture? But we are, it's just slow time. Okay, so it is row length -2, column -1. Okay, so it's bottom right. So starts equals this, and our length -2, world 0, length -1. I forgot my C. C colon, there we go. So boom, we have multiple starts. We just pass starts.map, start, bottom. There we go, and yeah, Dijkstra 2. I'll just go there and make it. Theoretically, I should just be able to modify this as is. Start has nothing else to do but the literal starting position, so I'm just going to use this one. Congratulations, you are a variable thing. How do we do that? We do it like that. There we go. For const start of starts. Name that to plural. Boop. Boop, boop. Boom, that should be it. I really hope Dijkstra's algorithm is chill with that. I gotta spread that, of course. Okay. Hey, 1's not broken. That's good. Let's see what 2's feeling about. Only 2. Expect 21 to be a big number. 21 minutes. That's actually accurate. Okay. What are you telling me? Oh, come on, Wallopy. Don't hide my output. 2589. Watch that space. Answer length, but first character wrong. Okay. Concerning. So let me go through my assumptions. It's working on the test case, which is the really scary part as usual. Dagnabbit. It is bottom right, correct? That is our entrance. That is our entrance. We can go through palm trees, right? Right. I did do palm tree permissible logic. You can go from palm tree. You can go to palm tree. These characters are both valid. Because flowable dot p flowable not flowable includes. I don't know, I'm just trying to make this a little better. While I don't have ideas, if flowable includes either of these, I mean, either of these are include flowable, really. Hey, look, it's still looking for the example and not the real one. I love it. Like 2589. Yeah, that's what I tried. You don't like that. All palm trees on the second farm. So what I'm doing is I'm returning the one that is the last one reached. Interesting. Okay, let me target the example. So what is the last one reached? Furthest. So yeah, it's basically eventually we hit 21. So 0, 1, 2, 3, 4. 4 is the one. 0, 1, 2, 3, 4. 317, and then we try a bunch of other ones. So 317, 0, 1, 2, 3, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So you're the last one reached, huh? Okay, I mean, I guess that makes topological sense. You're the last one reached. Am I doing some off by one stuff? Because I need to not touch it, but get water in that position. I need to flow into it. Yes. So yeah, I'm just gonna look at this top left, bottom right, see what their distances are. Console log tree, and just give me the distance while I'm here. So I want to see what they are. So the top one is 3, 17, 15. So 17, 16, 15. So I want 15, then a high number. Oh, row 7. So row 5, 9. It takes you 5, right? Yeah, so 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay, I mean, it doesn't start. 1, 2, 3, 4. Okay, you don't count from there. It works. Is there any time delay with permeability through a palm tree? 1, 2, 3, 4. 4. Yeah, you're flowing just fine. What have I done wrong? Do I have to start visualizing this thing? There's a lot here to visualize. I'd rather not visualize this thing. It doesn't even fit on the screen, crying out loud. Okay, it's basically visualizing all the distances that are covered. I think I just find this. But I think I fooled around on something. Yeah, this is working. Column 0. Length -1. I mean, we're going to do this, it's going to break, right? Yeah, it broke. What about conflicting, right? Multiple furthest? What do we do for that? We don't care, I don't think. let's transfer. Let's just see what we get, right? So, I mean, we're getting, my computer's eating itself. Cool. There we go. Yeah, that one didn't want to show up. 2, 5, 8, 9. That's what I tried. Okay. Guess I'm just gonna have to visualize it. I mean, I don't know what I did. Everything will be irrigated in reasonable time. 2 points on opposite sides simultaneously. Proceed as follows. I did that. Okay, how would I visualize this? Let's think go into Dijkstra's is the one. So as we update this, yeah, I mean, this is exactly what I do. Yeah, you just go through all the unvisited ones to eventually visit them all. Trying to think. Yeah, trees are P. Okay, I'm not looking at that one. I'm looking at this one. Anything special about this input? Just for good measure, right? And after this, I will visualize it. I'm trying to put it off, but I'm not thinking of anything else in the meantime. 2589. Okay, it doesn't like me. Let's start looking at it. So we're not gonna want this console log. When we hit distances, we're gonna want. I mean, technically, we're just gonna want to log through every distance, right? And then as it increases, go through it. So it's gonna be a for loop from smallest distance to largest distance. For cost frame, well, let frame, let f equals 0, f less than equals math.max, distances. Okay, let me just do another thing before I do this. Let me make sure the furthest is all these, right? What does this do with this? How much time to reach all palm trees on the second farm? All palm trees retrieval after 21 minutes. Yeah, I don't see it. I was thinking about trying to do something different for the furthest bit, but not treating me well. Math not match. Hopefully there's not an infinity still line in there. I think it's equal to. There we go. Okay, so we should go through them all and get all the things. For cost key in distances if hold on, what am I doing? Key equals value if distances key equals frame world cost RC equals key split on that bar map back to a number RC equals a little water thing. Well, if it's a palm tree, if it's not, it's another thing. Equals a dot, otherwise a lowercase p. Sure, I guess. So we do that, and we do that for every frame, and then we just log the world, I guess, right? So we're gonna need wall-based stop because it's gonna start eating things up. Clear console frame. Let's go ahead and get a label on that for goodness. Well, F. And then let's log the world. Let's see what we get from this. So let's get jest back, or vtest rather. I think we're going to hit both. What? Hey? Oh. Helps in the right folder. Okay, lots of logging. We're hitting some stuff. Let's use our eyeballs. Yeah, the colors really would help. I mean, obviously in this example it's hitting correctly. I guess I'll look through them all. Make sure they're good, right? So 0, 0, 1, 1. I mean, yeah, they're all flowing exactly as I would anticipate. Something's obviously wrong, though. So yeah, I think this is what we're going to do. I'm just going to put my breakpoint right here, right? I'm just going to run it on the real one. Let's do this. Oh, it's because I have the only... get away from there. Let me back in. Hey, what part of breakpoint, the word debugger, don't you understand? Because I'll put one there since you don't listen to words. Dang it, I'm the idiot. It was me. Go ahead and just run. This console's in here too. I was the idiot. Okay, what's part 3? No entry points. Groundwater under high pressure, so dig a big well. Water evaporates significantly, flow through channels. Dig out one of the channels for some of the time. Oh, so I just dig at one place, right? So I just try every place. I'm like, hey, great. So I think the inversion would be to Dijkstra from every palm tree, because there are less palm trees than other ones. And add up all the locations and find the smallest one. I think that's what I'm going for. Let me put the right number in here. Stop being an idiot. It always sucks when it's like, obvious thing was obvious, but I didn't do it. I should have checked it too. Okay, let's not make that mistake again. We're going to make a copy, and we're going to change everyone to use the copy first. Look at that. We remembered. Okay, so let's do this. Let's go ahead and reinvite Wallaby to the show. Give me my example. Let's take this one. Assuming these give a total of... This is the optimal point for digging. Okay, so yeah, 12 minutes. So just figure out the optimal point and be digging. Okay, yeah, we got that. I guess to infinity, obviously. So let's do this. I think it's Dijkstra to any place. So we have the graph. So we have const tree. I don't think I need. It's like looking through my full plan. It was Dijkstra the tree, and then add them all up, and then average the lowest. Because you're saying dig where? Dig here, right? So I think distance from there will be 1, 5, 7. I don't know. I'm gonna go for it, and if it's less efficient, then I can just do this all without building up the memory. Your distances equals here. So for tree of trees, let's do that again. Drop that. Oops. Tree distances from tree plus tree.c equals Dijkstra graph tree dot r plus tree dot c. I think that's legal, right? Looks pretty good to me. Let's stop looking at all of this. I need to do that eventually. Return 0 for now. Okay, so we have tree distances. If I look at them, yeah, look at all these tree distances, all this memory, nom nom nom. Now I just need to add up all the distances. Sum cost all distances was here. Const key and tree distances for const distances for tree distances, key for const lock of in distances, and then it'll be sum to distances lock, sum distances lock, or 0 plus distances lock, just like that. And that should give me all of them. Yes, it does. Now I just need to find the lowest, which according to it is 0 1 2 0 1 2 3. So 2 3, right? So 2 3 is 12. That's a pretty low looking number. Let's do it. Return object entries summed distances, sort a b. We do sort a, well, b minus a. I need to go small to large, so a to b. And then what do I care about? What I care about is the sum of these times. Ooh, that's interesting. That's interesting. So I need to go from the position back to the freaking palm trees? Okay, I can do that. So I need 0. I need the entry. Dig lock. Yeah, so that's giving me other stuff too. But I got the dig location, right? And then I got cost. So I'm doing this again. I'm doing the trees also. Just doing a different thing. 0 total distances, not from here, from dig lock, total plus equal distances to that particular tree. Was there anything else I needed to add? Oh, that one's happy. I'm angry about this because TypeScript. Is it just TypeScript or is everything script? Cannot read properties of 0. Would help if I had the right input in there. Let's do it. Okay, this is either working or it's killing my computer. Computer don't sound very happy, but we got something. Cannot read. Okay, Wallaby, are you failing or cannot read? Oh. Okay, cannot read of undefined. Yeah, so we need to focus and figure out what is up. What's this yellow thing want? That's not, we don't. Okay, let's just look at summed distances. What do I need for you? That's a little help here. Get back in there. There's just a lot of stuff, I think, honestly. How would I... So I'm building up a lot of memory. So it's either memory or it's the computations. Let's tell Wallaby to take a vacay. Is there still a console log? Something's showing up somewhere, but let's take that vacay. I'll debug on it myself. Don't know why that's still doing there. Okay, so how many trees we got? We got 193 trees. You got this. Okay, like a second for each. We got this. We can reduce memory impact with this. Let's go for the reduction of memory impact. Sum to distances. Yeah, bring it up there. For lock and distances, put that back in there. There you go. Yep, now you do it in line. So you don't have to do it after. My debug breakpoint is just gone to the void, so I might as well kill that. Let's make sure the example still lives. Good. Less memory, still computationally, well, computational. Drop tree distances. T. T divided trees length. Sure, now we have a percentage times 100, make it a little easier to read. Okay, let's see. We know this is faster. I think I have the only where it needs to be. I don't know if I get output here. It's a trying. Hey, no output, huh? That's okay. It's not really. I kind of wanted that output. Okay, fine. Put a breakpoint there. Debug on there. Right, it's only 190. It's not that many. Alright, so if we look at this. Hey. Yeah. So I think we got this. Let's just let it run for a bit. So it's like 200 seconds. It's like a 2-minute run. So I do have to be patient, unfortunately. Which, if anything, would be better on a run. T14. Okay, yeah. So stop this. Let's do a real run. So we're literally just timing this now. So quest 3. Let's bring it out. Where is it? Here we go. Boop, boop. Back up there. We got it. And I've added a bunch of extra white space. I hate that. Boop. Okay, we have it. We're ready to hit it directly. So I have that console logged in there, so we will get progress. Right. Thankfully, we're not going to hit a memory limit, I believe. If anything, it's the same process. So this is linear, thankfully. I'm looking at the wrong one. Where the heck? Yeah, so it's linear. It's inefficient as heck. While this runs, which I believe it will give us the right answer, what would be the efficient approach? I know this is more efficient than looking at every spot and trying the distances, because that is thousands, because there are multiple diggable places. What might be more efficient is starting at a different place. So looking at diggable positions, finding the average middle of the map. That doesn't really account for traversability in walls, though. I mean, it's not fast, but I think this is about as optimal as I personally will be getting here. Doesn't help that I'm not writing those optimal language for work. I think it's good. Can I target this for timing improvements? We are creating a graph and not like making a lot of memory up front instead of dynamically accessing it, but max this out a lot, so this is memory, not time. This keeps getting recreated. Yeah, it's Dijkstra's. I don't know what more I can get out of it. Now, if we're going to start getting into some kind of feedback loop of this not working because of tiny error A, B, C, and D, we're going to have a challenge. We might have to start dumping state to shorten that loop. We got 200 things, about a second each. I'm not seeing anything better, to be honest. Well, I got like 20 seconds left. It shouldn't be getting slower. My memory, it's going up and down like a spike beach ball, but should not be going leak-wise. Moment of truth. Don't crash, son of... Okay, that was good. Okay, I was about to be like, no. And I was like, nope, we're just dealing with the other error. Oh, and it's wrong? No. We did all that, and it was wrong. Now, the only thing I changed before I sent it off was me doing the optimization. I did not test the optimization against like real tests before I did this. So there is a nice scary possibility that I just burned 2 minutes without testing first. Still works. Well, nothing's working actually. Excuse me. I think I killed the file, so it's like not seeing it because my removal of the import. Let's see what it sees now. Hey. Oh, are you going Wallopy? Because we're a little worried there. Part 1, easy win. Part 2, easy win. Part 3, example. Still works. Dang it. Okay. This is the thing I was worried about. Iteration with this much of a time expense. So yeah, this is going to eat me up alive of time. We're going to do some caching. So basically, graph is unchanging. We're looking for the starts. So cost key equals join if f exists sync cache. I guess it's this way because I'm on Windows. Cache distances key .json. Let's get the path in here since we're going to use this a bunch. Come here. Get in there. There we go. If it exists, then use it. If it doesn't, save it. TF8, and I need a JSON parse that. Thankfully, I think the infinities will be fine, but if not, let's hit that one up. Otherwise, we'll save it at the end. So that'll be file JSON stringify. Well, I think I put the wrong thing in the wrong place. Path null2. Might as well make it pretty if we're doing this. So let me think. npx feed test run dot. I'm going to make a cache folder. Let's see, this should generate, right? No such file or directory. Well, yeah, you have to write one, you idiot. What's wrong with you? No such. Okay, are we doing too many crazy symbols? Do you hate symbols? I can get rid of symbols. Replace all of your vertical bars with underscores. Yeah, what do you want? It's a right call. If it exists, do the thing. Otherwise, you're writing to the file. What are you doing? 18 cache distances. CACHE. Okay, let's figure this out. Let's figure this out. Parent path doesn't exist. It's pretty existent to me. But sure, let's fs megdir cache. I don't know what you want. Vector multiple arguments. What do you want? Oh, I'm gonna have to do a megdir sync. Sure. Weirdo. File already exists. I could tell you that. This is because I'm using backslashes and it's like, well, yeah, but you. What is this weirdness I'm dealing with? It's a real folder. Fine, am I doing it this way? Tried to do the right thing. Is I'm being punished for doing the Windows thing? I'm losing my mind here. I did all this to try to get some easy debugging here, and I just face planting. Oh, wow. Yeah, this is just literally throwing me off. Can't write a simple freaking file. You know what? Drop the cache folder. Let's blow it up. Fine, we'll do the bad thing. Okay, finally. So it's characters in here. You just absolutely hate them. Let's do it up here, I guess. I wanted to just write a file and read a file. I know. Distances S key in old distances return. So we want this bit up here. There we go. So we'll do that. We'll make a thing if it's in there. If it's not, otherwise. Distances S key equals distances, and great. You'll then rewrite the dumb file. All I gotta do is make an empty file. Boom. That's a valid JSON. You put it in. You write the file. It's not that hard. Now this part changes. old distances as key, not skip, whatever. Okay, we'll do this. We're running everything and we're hitting the cache for that one there. So we need to stop at this, because that just built a lot of things for two different graphs. So we need to do this. If graph JSON stringify graph hold distances, put that there, come on. Graph equals empty object. All distances, then we have cost old distances, which is all old distances, jgraph, because I've done that enough. Great, now we can just use this one over that one. It's great, we love it. And it's going to run. Now, I don't know if I have a logger in here. I don't, but it should allow us to do... Yeah, it's building a huge JSON file. I think I need to clear this out. There we go. Let's put a skip on that one. Come on. Or an only on this one, rather. Boom, we did it. We ran the thing really good and fast, and we loved it. I need to make sure this is being hit. This isn't what it's supposed to look like. Excuse me. You had one job. Right to the thing. Oh, graph old distances, which is... What do we call this? All old distances. Yeah, that's gonna do it. So this is why you do test runs. Now we're gonna see an ugly key and then like 2, 3, 4, well, palm tree number of iterations. Okay, if it's reuse, right? Okay, we're seeing it. This is exactly what we want to see. Let's drop it. Which means now we just want to run 3, right? Yeah, we want to drop the only and just let it rep. It's gonna build up the cache, then I'll be able to debug it a little easier. Don't know what's wrong though. So there might be some other minimums. Might have to consider other minimums. So dig looks. Right, so we did the thing, we did the sort, that was the important part. All looks, and then the least one is 0, 0, so cost dig locations, which is all looks. Well, it's filter pair, well, entry technically, and then it's entry equals all looks. That's filter actually. There we go. And now we go for each one. So for cost location of dig looks, and we figure out what's the best, which is the least. So best equals number dot max, and then down here we return the best. Best equals math dot min, best in total, right? And we'll call you look. Oh, right, because it's a thing. I guess we'll take a map. We care about the locations themselves, which are right here. great thing is I know that this is just piling up the data. I think looking at it will kill my computer. Yeah, I shouldn't have done that. Now, there's a danger here. I could stop it, and it could be in the middle of a JSON write and eat my life up. Thankfully, we know this is a 200-second run, and we do need to run it no matter what. So I'm just going to let it keep going. The only bummer is we don't get any output. Let's risk it. Boom, properly saved. We lucked out 152,000 lines, and VS Code has abandoned us. Nope, we're back. Okay, good. That console log would be really nice if it showed up. Let me const fs require fs, drop these, and just go straight for the one we care about. Go back into rapid debugging mode where I can get console freaking logs showing up. And yeah, this will work. npx tsx quest run for me. Look how fast forwarded we did. Okay, so we're in the 60s. So we made a potential fix to it by considering all of them with, hey. Oh, right, we don't care about those. We just care how long it takes to get to the trees. I'm trying to think. We could make this Dijkstra a little faster by being like, hey, once you make it to all the trees, stop caring. I'll actually disagree with that now. Because that means it will skip some tiles, which will throw their averages down. And I really am just doing the straight up average here. Well, I'm not even doing average. I'm just doing the lowest sum. Maybe I should be doing average, right? Summed distances and then average distances. Can't hurt to try. Cost average distances. I think it will make 0 to no impact, but I'm not doing anything in the meantime. For cost lock in average distances equals, well, lock equals average distances, lock divide by the number of trees. That's what an average is. Sum divided by a total, or count rather. And then I guess we could use this. I don't remember the last number. It's the same as the last number. Hey, let's go for the averages. What's the worst we got to lose at this point? Oh, we found an infinity in our thing. Interesting. Oh, I just made it. Hey, I didn't put anything in here. Sum to distances. That would help, putting some numbers in the thing. More, it's gonna be the same though. Dang it, it's the exact same. Okay, thankfully we have something to look at. I think my underlying approach might be wrong then. Or at least my assumption of it. Target every position. I say, hey, oh, wait a minute. If my position's under a tree, that's illegal. I have to filter those out. So all locations dot filter entry trees sum, not sum, t plus r plus t dot c triple equals entry 0. If this is it, then I'm going to really disappoint myself for never actually looking at where I'm digging at. Oh, I swear if this works. Dang it. Ah. I dug under a palm tree. That's super bad. It's so obvious. Okay, we're working though. We did it! With a little bit of caching to help me run things. We did it, and I bet we didn't even need all this. We just needed to not dig under a freaking palm tree. So I will capture that. Add initial 18 solution. We did it. Okay. With that, it's time to walk through this baddie. So this is a pretty fun one. We're given basically a map and a bunch of targets we must reach, and we are the water, and we start in the top left position or the bottom right position in part 2, but we start in the top left position, and we must get to the position of every palm tree, so not up to it, and basically hydrate them. Now, the distance is all one, so there's no weights, there's no difficult terrain, there's none of that. It flows at 1 block per minute from every existing water block. You can flow through palm trees. Again, no penalty, no distance, no alternative weights. As you do that, time will flow on, a minute per block. 11 minutes for this example, because by the 11th minute, we hydrate the last palm tree, and we win. Which we just use dexterous for, and we're like, okay, which of these is the one that takes you the longest? You win. Next is just you get water flow from multiple sources. Dextra is perfectly compatible with this. That's all we used. You're supposed to report the time in which the last palm tree receives water. It's this one, by the way. Part 3 was the fun one where you have no entry point, but you can enter under any of the dots. Specifically the dots. So you must find the best entry point that will allow you to water all the palm trees in the least amount of time. So that's basically the one closest, like where the distances to all the palm trees is the least. But remember, this has to be a dot, not a palm tree. You can't dig up a palm tree to supply water. That's very unhappy to the palm tree. The palm tree doesn't appreciate being dug up. In this one, you sum up the time it takes to get to each palm tree instead of something else. Instead of returning the time it takes to get to the last palm tree, to all palm trees. Yeah, that's the challenge walkthrough. Honestly, relatively straightforward. I just goofed basically all of the things. First, by not putting Quest 2 on my Quest 2 function and digging up a palm tree. But yeah, it's refactoring time, and this is going to be a good one because I believe it's relatively the core functionality, basically the same with very slight differences at the end. I did do some caching, which was cool of me, which, Oh wait, the caching is literally only for my development purposes. So the caches have 0 impact on the whole thing. So I'm going to keep the caches for now. I'll remove them at the end and do a final run. So solve quest. Technically you have multiple starts. So first one I'm just going to go for is replace this with solve quest. And you have multiple starts, which you'll take as this. Starts, which is just a location array. Boop, right there. Ooh, you don't have access to that there. So let's remove this.
Yeah. Disagreeing about how to actually implement this. I mean, I can get rid of that part. Okay, yeah, so same call, whether you have starts, whether you don't. What you're returning is different, though, and I don't think I need all this fanciness here. You don't have access to this information until you do the splitting and all that stuff. We just add two booleans. Start top left, boolean, start top right, bottom right, boolean. There we go, we did it. And we'll just add these as conditionals. If, whoa, that's not the thing. If start top left, starts push, hey look, you're doing a thing. Otherwise, if start bottom right, starts push that. Okay, I love this. We have our starts being initialized. Boom, your location array. We detect all our trees, and then we go and we build our graph. And you know what? Let's go ahead and now I like this separation of concerns. So flowable. This isn't a word. Permeable. Permeable. Sure. That's the word I wanted to go. Permeable. Love it. These are things that are permeable. So as you're doing this, you're building the graph from key and graph. No, build the graph. If it includes the thing, congratulations, you have a 2 key that you literally only use once. Let's just shove it in there. And new row, new column, you don't. You use it twice, so you can keep it. Okay, I like it. Okay, big fan. If distances, gotta do that. Furthest, do that. Yeah, we could do a reduce over trees. I think this is perfectly fine. Okay, now for 3, we do a lot of the same, but then it's like, oh no, we don't have a start location, so we do a lot of other work. Let's see if 3... Oh, this thing's been dead. Hey, wake back up. Oh, you're trying to read files? How about you don't do that? Right, this is the I'll keep caching on it as long as I can thing. But you don't do that. Don't worry about it. Ooh, it's running something. Alright, do I have this sub this still sitting here? I do. I gotta kill it. With fire, kill it. Okay. Might have to reload. Okay, finally we're getting input back. Expected 3 arguments, got 1. True, false. Let's get all these in. True, false, and that'll be true, true. That's right. True, true. Yeah, we dropped the 2 back to a 1 like it was. I kept trying that one time. That turns out we don't need that trim. You should call your right functions. Okay, and then quest 3, we're gonna drop that to... We'll leave it at 3, because I believe the 1 logic can be reproduced or reused. So let's leave it there. Let's move all the 1s. Because we do eventually need all the distances, but we don't have a start location, right? So let's find trees and generate graph. So this is really just a parse world thing again. Let's go for it. Function parse world. Notes string. Do I need the starts? I don't need them specifically for this. So let's do it. Da-da-do, da-da-do, da-da-do. And we drop the starts. We don't need them. We don't actually need the world either. Do we? I'm looking at the wrong place. Do we need the world? We do not need the world. Love it. We just need the trees and the graph. Now, did these get typed? Very sad. Greatly saddened. Record of string to record of string. I mean, I think that's just a string array, actually. Boop, boop, boop. There we go. This is a location array. Love it. We have our world parsing. Let's get our world. That depends on the length, right? Width and height. Let's return width and height. Width world length. Well, it's world 0 length. Then height world length. There you go. So we'll get all that for you. Const graph trees, not grease, trees with height equals parse world notes. We have all of this, and now it's just -2 and width -1. Drop all these. Nom, 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 nom. Boom. So we do that. We build our starts. Big fan. Yeah, I think this is good. I think we can even further this further by generating a start and then have this do its thing. But let's one thing at a time. Const equals parse world. There we go. Dropping all of this unused stuff, and the chaos begins. Okay, so I got 3 sitting right here. I also have the 3 notes, which is technically cache acquiring. It's gonna be hard to test that against this. What I'm trying to do is I'm trying to say we don't need all this. Won't be able to do that until I run it again. I can't run it again until I turn the cache back on. So const acquire, because the cache only works when the real one is here. And in order to run that, I need to bring this call here back into play. I never put the real value in. That's awkward of me. Oh, what the heck? Great, I have that. I have to go dedent all of this now. Okay, we have it. I should be able to run that directly. Power of cache compels. Number is good. Okay, so I've done this. These things are working. I need to look at console log dig locations. I think there should only be 1. That's only my suspicion. There is only 1. Okay, I love that. Can I go back to the sum to distances? I know these numbers are technically larger, but I don't need to make a whole nother data thing for it. Yes, I can. Okay, I love it. Didn't need those. And since it's only 1 dig location, then I don't need a map. I can just 0, 0. And we'll just say, hey, look, it's a dig location. Drop that, drop that, drop that. Return the total. Drop those. Save, rerun. Number's still the same. There we go. 2295. 2295. Loving it. So I did need to sort and I did need to filter. The world would have been nice actually to do this, because this is an expensive lookup. But I'm here. It's fine. Okay, we have all locations. Make sure you're all equal to this bottom. Yeah, we didn't need that either. We could just say all lokes 0, 0, because there was only ever 1. which means dig lock there. I love it, because now what we're doing is we're saying, okay, we're doing a little different thing here. Between 1 and 2, we need to calculate our start position by doing this fun magic, which most of it's in the Dijkstra, unfortunately. Thankfully, I don't need this log anymore. It's just for that. Or just for progression, rather. For location is distances. Some distances, sure, alright. Yeah, some distances is probably fine. What are we calling these? These dots. Channel distances. There we go, because that's what they are. They're distances to a channel. And we go through them, we sort them, we filter them, and we get 0, 0. So we need 1 for sorting. We need 0 for... Well, we need the value for sorting, but we need the key, because that's actually what we care about. We filter... Yes, we don't need to sort, we don't need to filter. We can do a reduce. Am I with this? Dig location, distances, and then this just gives us the total distance to every tree. But this gives us the distance to the furthest tree. We want both information, honestly. So what's this number they call it down here? Time to reach sum of times all time. What a weird thing. I just want all the distances, to be honest. So let's make a function of that. Function get all tree distances times all tree water times. There we go. We just want to do this, kinda. Okay, so we need the graph. We need the starts. And we need the trees. That makes complete sense. We have that. Then effectively we are returning trees.map tree. Ba-da-boop. Ba-da-ba. Yeah, that's what we're doing. And for some of them we're doing a reduce. For others we're doing a not. I like it. Let's type this back up. Starts, which is a location array. And trees, which is a location array. Love it. So we have all this, and we're just going to want to get the largest of it. So return math.max, spread up this graph, starts, trees. I love it. We can even get fancier for this, but I like this perfectly fine. Then this one, we just get the sum of them. So return graph starts, which is dig lock trees, and then reduce, well, trees, reduce a b, just like that. Why are you not happy? String is not assignable location. Oh, well, yeah. And the types are being a little wonky. We will fix this. This is gross. So I'm doing it twice. Can I just do it here? Yeah, I'm just gonna do it here. So congratulations, you're a string array. Boop, there you go. Less work for me. You will just take that and be happy with it. You're just summing these all together. You couldn't care less. We're not looking at that view because we're inlining this. Channel distances for every tree. Yeah, this is exactly what we want to do. Now I could get fancy. It wouldn't be that fancy. It'd just be inlining. I can go through entries. will be object.entries, which, let's not get too expensive on there. Dig location. Let's make it a little more readable. Sort filter, right? Yeah, that makes it so much better. Make sure this still works. Number still numbering. Okay. I'm liking this. It's basically a call to your parser, and then a call to get all the trees, and then do whatever you want. And the special bit is you in the middle. Particularly, you have customizable starts, and you gotta figure out where your start is, buddy. Which is right here. Okay, I'm liking it. Gonna de-inline this. I'm going to decache the entire thing. And then I'm gonna give it a final run and say goodbye. Jump, 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 jump. Jump, jump. Okay. Feeling pretty happy. Gonna flip that back to infinity. Because it does make the comparison easier, I believe, in the deep, deep dark. Don't need that many lines. Okay, let's go through it one by one. Part 1, beautiful. Part 2, beautiful. Part 3, example. Ooh, 1.1. Got fast, didn't we? Not gonna touch that. So we call this optimize 18 solution because we know you're gonna take a second. So I'll let you run here. And we know it works. We just don't have cache. So I'm gonna commit it as is. If it don't work, you're gonna see a real awkward clip of, hey, we're fixing something that lasts like 30 seconds at the end of this. But I am confident. So confident I deleted all the old caches, as you saw. So while that runs, let's walk through the solution one last time. So for both of them, we have to parse our world. So we go through here. We turn our world, which is a big string, into a matrix of characters. And first we hunt for all the trees. So we go through every row, we go through every column, and as soon as we see a palm tree, which is the letter P, we push its location to this array. Then we need to build the array of where you can go from other places. It's not an array, it's a map with an array within it. So we go through every place and we're saying, hey, if this isn't like a place that water can go, if it's not permeable, then skip it. This mainly pertains to walls. We're skipping walls. And then if it is, then we need to generate a key, make sure that key has an array in our graph. If it doesn't, make one, and then go and arrow for cardinal directions. Up, down, right, and left. We need to figure out where our new position is, and if that's a permeable place, which we do the same before, but with optional chaining, because this row, like we're going in all 4 cardinal directions, we could go off the world entirely, which would mean this would be undefined, and we'd be accessing undefined, which would throw an error, but with this optional chaining, we're like, hey, don't worry about it, just turn into undefined, which permeable would not include and would be false. But if it is true, it is something that we can go to, then we add, hey, from this location, you can get to this location. And we encode that with the bracket, just because it's a nice, cool character. And that allows us to build our graph for Dijkstra. We return it, return the trees, and we return the height and the width, because some other things need that. That's for all of them. Remembering and focusing down on part 1, though, the conditional is that you start in the top left corner. So you have that up there. You will always be starting in the top left corner. So this always exists. I don't need a conditional for that. don't know why. I was just, I just didn't have enough booleans in my life, so I was like, another boolean. I need to control everything, even though if both were false, that would mean there were literally no starting positions, and we don't have an example where there's a bottom right only. So yeah, slight tweak there. We always start in the top left corner. For part 2, we start in the bottom right corner also, but let's not worry about that. Then we get all the tree watered times, which is the time it takes to water every tree. We pass it the encoded coordinates of the start locations, and then this is really just calling Dijkstra, which gets us the distances, and then going over each tree and returning the distance to that tree. Now, I'm not going to go over Dijkstra. You can find another YouTube video that does this well. I'll just go over what my slight tweaks I made to it. I've copied this like 3 times with everybody codes. Aside from adding types and adding support for multiple starts, which essentially just sets each start to 0 instead of setting one start to 0. I have no weights, so it's barely even Dijkstra's, so it's +1 instead of plus whatever the weight of the edge between these two nodes is. Because all weights are 1. It takes 1 to do anything. After Dijkstra, we are given all the distances. I already told you about the mapping. In this very particular part 1, we're getting the largest one, so it's math.max. Spread the distances gets us the the highest distance, which is the last tree that gets watered. Part 2, you can start from the bottom right. That's it. That's the only change. You have an additional starting position. Dijkstra is fully compatible. It barely even notices this is an impact to it. You can have many starts. And then we go to part 3, which we still do parsing of the world, but then we call Dijkstra from every tree. So we get the distance from every tree to every other location, and then we add up all the locations, like how long it's been to every single one. So I'll go through the example here. There are 3 trees. Let's say it takes 1 to get here, 1, 2, 3, 4 to get there, 1, 2, 3, 4, 5, 6, 7. So 1 plus 4 plus 7 is 5. It's up in the teens, and that's that value that has. Now the rest of them, since they are further from more of the palm trees, they're going to have higher values because they're harder to get to. Now this one, it's like, oh, okay, this one's got like a 1 from this palm tree, but from both of these palm trees, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's 7 plus 11. We're already at 18. That's higher than it was over here. So you can see that that's the way we do it, the way we figure out which dig location is the closest, because it's the one that added up has the least average distance to any palm tree. Which is what I was doing before, actually calculating the average, which is the number divided by however many. But you can do it with the sum just as well. We could use the averages to do some cool color coding of being like, oh look, this one is much further away than the other ones, but that's a visualization fun thing that we're not doing. So once we do that, which takes an extensive amount of time, which, as we can see, 206 seconds, which is about like a second per tree, because that's how many trees we have. I'm gonna let that go again. Once we do that, we go through all of them. We sort the smallest to the largest because we care about the smallest because it's the one that is closest to all the palm trees. We make sure that this smallest location is not a palm tree in itself. That's illegal. You can only dig up a channel on a palm tree. So you gotta add this filter here, which I didn't have. Then you get that entry, and then you get the key from that entry. That's what the double indexing is for. And that's your start encoded coordinate. We just get the times from that start encoded coordinate to every tree, and we add them all up, which is what part 3 wants. Yeah, that is everything. As always, it is a pleasure. This was a pretty fun one that I did pretty okay on, minus the goofs, which those are always fun to live through. Really enjoyable. Until next time.